Hello everyone, I am Pragya Srivastava. I am here to record a lecture on VLSI technology. The course code is KEC 50053 and the topic which I will be covering today is oxidation. So before we start oxidation, we must understand that what is the need of oxidation and is there any step which we should take before doing oxidation, or we can directly straight away start with oxidation process. So oxidation is a process where let's say we are having a layer of silicon and we want to protect it from environment, and we just want to have a layer of insulation. So we can have a layer like silicon dioxide on the top of silicon. But at the same time, what is the purpose of doing epitaxy? That should also be studied. So once the ingot is grown, ingot is nothing but the seed, which is the material, which is the geometrical nomenclature for the seed, which is further cut down into wafers. So once the ingot is grown, it is cut into slices and the resultant thing is called a wafer by a diamond cutter. These wafers are chemically and mechanically polished, that is chemi-mechanically polished, to remove surface damage. So we want to remove such kind of surface damage. It means, let's say we are having a wafer and let's say that is the composite structure, that is the site on side a wafer, and the wafer would be like this. That is a wafer. So correspondingly the size which I have drawn for a transistor is quite big. Let's consider if it is a wafer, we can have a millions of transistor on the same wafer. So we are talking about this wafer, and there is an ingot. This ingot can be seen like this. This is the shoulder, neck, and then this is the ingot, which is using a diamond cutter. It is sliced and then we get a disc-like structure here, which is called a wafer. So for many applications, wafer serves as a mechanical support on which one or more layers of material are grown. So the process of growth by which the amount of material is set down upon the crystal while the overall single crystal structure is still preserved is known as epitaxy. So from where this word epitaxy comes in, we have epi means upon and taxis means ordered. So if we just mix these words and then we try to understand, so when we want to order upon, when we want to layer upon, epitaxial layer can be arranged on the top of the bulk crystal. So epitaxy involves extension of substrate lattice by overgrowing the layer of identical or different material. So we can have, when it is identical, we can have homoepitaxy. When it is not identical, meaning it is the two materials are different, we call it heteroepitaxy. So moving just ahead on this, for fabrication of various applications, growth of bulk silicon crystal is not enough. So just as an example, BJT, in BJT we can have a NPN or PNP type of configuration. So N crystal should be grown on the top of the P type bulk. So or vice versa, P type crystal should be grown on N bulk. So this is how we can justify the process of epitaxy. There is a difference between bulk crystal growth and epitaxy. Bulk crystal we obtain from ingot and the thickness is like 500 microns. On such bulk material we have to grow much thinner layer, and which is like up to few microns. So a thin crystalline layer will be arranged on the top of bulk substrate. This is called epitaxy. So I think this was all about epitaxy. We can have a pictorial representation where we can see that the wafer with an NPN, we can see NPN, discrete transformation fabrication, epitaxial wafer. So this complete thing is an epitaxial layer. This complete thing is an epitaxial layer, and the wafer is here. See, the wafer is here. This is the wafer. We have written also. Wafer is this, and on the top of the wafer, like let's say we have a wafer. On the top of the wafer, let's say wafer is N plus. I am growing a layer which is N type. In this N type layer, what I am doing is, I am making this P layer grow. On this P layer, I am making another N layer. So this is what we have grown epitaxially. So this alone is wafer, and then this complete thing is epitaxial growth. Now, we have to see what are the types of epitaxy. As I have already told, homoepitaxy, when the material on which we are growing and the material using which we are achieving the epitaxial layer are of same type, so we call it homoepitaxy. Let's say for example in BJT, P type silicon crystal on top of which we grow, and N type epitaxial layer, but both of the item are silicon only. One is P type silicon and another is N type silicon. And in heteroepitaxy we use like the two materials are different, so we can have silicon on sapphire, where sapphire is nothing but aluminum oxide, Al2O3. So the two are like the crystal lattice structure, everything is different. So when two dissimilar material is grown on the top of another, we call it heteroepitaxy. So this is now the next thing for which this lecture is all about is oxidation. The most general use of oxidation is to mask during dopant incorporation. So what is happening is, we have to put a layer of mask during dopant incorporation. Oxide is an insulator, and to protect the certain regions through which we do not want any doping to take place. So oxide is an insulator, and it helps us in such a way. We can open some windows in the oxide, through this doping will take place, and so the oxidation can be used as mask for fabrication process. What is actually we are trying to do? Let's say this is a wafer, silicon wafer. Okay. Now I want to add, let's say this is P type. I want to add N type layer here, but I know during the process when I will make this kind of diffusion or ion implantation, this N will not be limited to this. This N will spread up in the complete lattice like this. So instead of having this much of N, I will have this of N. So what will I do? I have to protect this much region here also and here also, because I want well only here. So what I can do, I can have a silicon dioxide layer on the complete thing. Complete thing can be coated with silicon dioxide, and only the concerned site can be removed using lithography. Only this concerned site can be etched using lithography. So this is, now if we study the first line, we will understand. The most general use of oxidation is mask during dopant incorporation. I was incorporating this N-type dopant. to mask the remaining sides. Oxidation is an insulator and it protects certain regions through which we do not want any dopant to take place. So, I don't want doping to take place here, I don't want doping to take place here. So, I will mask the remaining portion with silicon dioxide. We can open some windows in this oxide. Here we are talking about lithography. So, we can open some windows in this oxide. Through this, doping will take place. So, oxide layer can be used as a mask in the fabrication process. It can be used for surface passivation. Generally, it is used to protect junctions on silicon substrate. Now, it is a device isolation. So, it provides insulation between two devices also. So, what is actually happening? Let's say we are having two devices next to next. I am having another wafer and another p-type or another let's say it is NPN and it is PNP. So, we are having two BGGs next to next. So, we have to have a isolation layer, isolation layer in between the two. So, it provides device isolation to provide insulation between two devices also. So, it can be used as gate oxides for MOSFETs device. In MOSFETs, we have 4 terminals: drain, gate, source and body. So, when we are talking about the gate oxide layer, this oxidation can again be a process using which we can realize gate oxide. So, this is another pictorial representation where we can see that oxidation over silicon interface. What is actually happening here is, we can see that it is a silicon interface, it is a silicon wafer here, and on the top of this we have introduced an environment of silicon dioxide, and in this silicon dioxide what we are actually having is silicon is added only in this portion, it diffuses in the remaining portion on its own. Silicon is added only at the top of the portion and it is diffused on its own. We can see that it has entered into the lattice on its own. So, this is how we can have the presence of silicon dioxide on the top of the wafer. Oxidation process. We can see that in the previous diagram also we had this thing and we called it as a wafer. So, original wafer was this. Layer. So, once I have added silicon dioxide, once I have added oxygen, this silicon oxygen will start reacting with the silicon interface itself. So, oxygen reacting with silicon, it will create silicon dioxide. So, silicon dioxide will be created at the top also and at the bottom also. So, we can see that the boundary shifts. This is the amount by which the junction has shifted. We can see that we have come down to here. This is now silicon and above which we have silicon dioxide. Now, studying into detail about oxidation, the oxidation process is chiefly used to form silicon dioxide, already studied. Then we have types. In this types we can have thin oxide and thick oxide. So, to grow thin oxide we have a different kind of oxidation, to grow thick oxide we have a different kind of oxidation. So, basic terminology is different. Gate oxide layer is a thin film under which channel can be formed between the source and drain. So, let's talk about a MOSFET, and here in the MOSFET we have, let's say, Then I am making straight away the metal contacts. So let's say this is the drain, this is the source, and then in between we will have the gate terminal. Let's say this one is the drain terminal, this one is the source terminal, and this one is the gate terminal. So what they are trying to say is we have two kinds of layer. So gate oxide layer will be somewhere here. So this is gate oxide layer, and then field oxide layer will be here. So field oxide layer will be here. Field oxide layer is a thick layer of silicon. Let me make it thick. Let me make it thick. Field oxide layer is a thick layer of silicon which acts as an insulator between neighboring devices. Okay, here and all I'll have another device also. So gate oxide layer is a thin oxide layer which is conducting channel can be formed between source and drain. So here we can see there will be a conducting channel between source and drain. Semiconductors can be oxidized by various methods: thermal oxidation, electrochemical anodization, and plasma reaction. Among these methods, thermal oxidation is by far the most important for silicon devices. So here we are trying to show a chamber. In this chamber, the process of oxidation will be carried on. So first we will try to understand the setup. There is a setup in which what we are trying to allow is we are just having a furnace, or we can this is the furnace. This is fused quartz furnace, and this furnace is just placed in between two heaters. We can see this is also a heater, this is also a heater, and here also we are having a heater. So this heater will of course maintain the temperature environment. So we have heater on both the sides, and on that we had a susceptor which will hold the wafers. We have a susceptor which will hold the wafers. See, these are the wafers. Okay. Now what we are trying, we are actually allowing the oxygen to enter. So once we are allowing it with H2O, it becomes wet oxidation, and if we are allowing only oxygen, then that is dry oxidation. So these are the two types of oxidation, that is wet oxidation and dry oxidation. So in previous also we have studied thin oxide layer and thick oxide layer. The two classifications are actually related also. And then we have this air enters into the ambience. Of course they will react with the silicon wafers, and then we have a vent using which the byproducts or the remaining unused gases can be pulled out to the system which is called the exhaust pump. And this is the overall setup where we are having a quartz tube, and this quartz tube is having wafers inside it, and on the top and bottom we have heaters, and we allow the required carrier gas, let's say at O2 or H2O inside, and they will react with the silicon surface and form silicon dioxide. And then at the rear end we will have a exhaust pump where the unused or the remaining or the byproducts will leave the system. So we will also have a fresh air here, so that the exhaust or the rear end of the setup is also always cleansified. Then we have to study what is dry and wet oxidation. See, when we have no water molecule, that is wet oxidation. Very much easy to understand. So when we are having this water like 2H2O, then here we have this arrow, SiO2 plus 2H2, and when we have only silicon plus O2, we have silicon dioxide. So this is dry oxidation, this is wet oxidation. Now from dry oxidation, we have certain properties which the wet oxidation will not be able to deliver. Those are, one is better electrical properties, better electrical properties. So this is why we are using in the gate region. If we can see that here is the dry oxidation which we are using. So here we are using dry oxidation. But it is wet oxidation. The electrical properties and the efficiency is not that high, but at the same time it is a faster process. So we get thick layer in the same span of time. Wet oxidation will give me a thick layer. So the oxidation temperature is generally in the range of 900 to 1200, and typically a gas flow rate is approximately 1 liter per minute. Oxides can be oxides grown in dry oxygen have the best electrical properties, which we have already studied, and considerably more time is required to grow the same oxide thickness at a given temperature in dry oxidation than water vapor. So when the water vapors are there, it means we are talking about the wet oxidation. So wet oxidation is facilitated by a higher speed, so that in the same time we get a thicker layer in wet oxidation, but not in thin, but correspondingly a thinner layer in dry oxidation. For relatively thin oxides such as gate oxide in MOSFETs, typically 120 nanometer dry oxidation is used. And however, 120 nanometer is like when we talk about dry oxidation, it is quite when we compare it with the wet oxidation, 120 nanometer is like quite less only. So however, for thicker oxides such as field oxides means the corner ones, 220 nanometer is in MOS integrated circuits like in MOSFETs also, and in oxidation in water vapor steam is used. So coming on to the chemical reactions, silicon reacts with oxygen to form silicon dioxide. The entire surface is covered with silicon dioxide. When the silicon chunk is exposed to the oxygen molecules, and the entire surface starts reacting with the oxygen molecule, and as a result we have a silicon dioxide all throughout the cross section which is exposed to the oxygen. So that is what they are telling, the entire surface is covered with the silicon dioxide. Some part of grown oxide is rising above the original silicon surface, and some part is going below the silicon surface. This can be studied in this diagram. Like the original silicon surface is here, so some silicon dioxide is at above the original surface, and while the remaining is below the original surface. So we have the silicon dioxide layer at the top also and at the bottom also, whereas the interface is somewhere in the between. Silicon is being consumed in order to form silicon dioxide. For analysis of area of silicon consumed, we can calculate molecular weight also. So using the molecular weight of silicon and oxygen molecule, we can have the corresponding area calculation as far as silicon dioxide is concerned. So now we have to study what is the kinematics behind oxidation. The oxidation can be done in various methods. If we boil the silicon in nitric acid, for example, we will form an oxide layer. This is called a chemical oxidation. So if we use silicon in an electrolyte bathe, let's say we are having a bathing chamber, where the use of anode and noble metals for a cathode in an electrolytic solution, and we apply a voltage between these two electrodes, then there will be a layer of oxide which will form on the silicon. So this is called anodic oxidation. So I'll repeat what we are going to do. We will use silicon in the electronic bathe, and then we will use silicon as an anode, and then we will use some noble metal for cathode. So this is silicon and this is some noble metal, and in the electrolytic cathode, in the electrolytic solution, we apply a voltage between these two electrodes. We will apply some voltage here, and then there will be a layer of oxidation which will form on this silicon here, you know, and that is called anodic oxidation. So this was, silicon was already acting as a anode here, and here was, this one was acting as a cathode, and this is nothing but the bathe, okay, or the electrolytic solution. But the better oxidation technique is thermal oxidation of silicon. The quality of thermal oxidation is way better than, is by far better than the oxides that can be grown on silicon. Therefore, thermal oxidation is widely used in VLSI technology. So VLSI technology uses thermal oxidation, and this is the most efficient method to grow silicon dioxide on silicon, where we can see that what we are actually having, we are having a silicon wafer. On the top of the silicon wafer, we are actually trying to grow silicon dioxide, and the two methods which we have studied here is, one is the anodic oxidation and another is thermal oxidation. So the quality of oxide layer is better in the thermal oxidation. Now the principle of thermal oxidation is very simple. We take silicon sample, put it in the furnace as we have seen, and we raise the temperature of the furnace and allow either oxygen or water vapor to flow in silicon, and the silicon will react with either the oxygen or the water vapor to form silicon dioxide. Let's say in case of dry oxidation, there is no vapor. We can see that H2O is absent here. So we are calling it dry oxidation. And in another case, in wet oxidation, we are having the oxygen molecule. So we are not passing vapor in the dry oxidation. Now the radioactive tracers, by the help of radioactive tracers, we have seen that it has been established that it is the moment of oxidizing species, either oxygen or water vapor, into the silicon that is causing the oxidation. So what is actually at the molecular level, what is actually happening is, with the help of radioactive tracers, we have found, we just observed it, that it is the radioactive tracers, and these tracers have found that it is the moment of oxidizing species which is actually helping in the process of oxidation. So so far we have studied what is the epitaxial growth, and in the epitaxial growth we have studied that how same type of or different type of material can be ordered on the layer of another wafer, where we have to have we can name it like homoepitaxy and heteroepitaxy. Moving ahead on this, we have seen that how oxidation helps in making P wells and N wells in N-type substrate of body. So specifically and exclusively making those wells only at the particular places can be only achieved with the process of oxidation, where oxidation will shield the remaining portion where we do not want the dopant to get or the settle on the surface of silicon. So what we are actually doing, we let's say we are having a wafer, and we want the p type of dopant added only at the site A. So the adjacent, which is B and C, should not be having the dopant. So just to cover and just to make sure that B and C will not get the dopant, and only the dopant will be settled at A. So just to mask B and C, we do oxidation. So as simple as that. This was all about oxidation, and we will come up with more informative sessions in my next lecture.